Very good morning, dear friends. Myself, Dr. Vikrant Sudhakar Palekar. I am working as an assistant professor in Gokhale Education Society's Arts, Commerce and Science College, Jawar, Palghar. Welcome in the second lecture series on the topic spectroscopy. In the last part, we have seen the introduction regarding the some spectroscopic terms which we should know, in which we majorly see what is electromagnetic radiation, what are the different regions in the electromagnetic spectra, and we have understood that the electromagnetic radiation is nothing but the energy which travels in the form of wave. And we have tried to also understand the different terms such as what is amplitude, then what is a frequency and wavelength, and based upon that the energy content, how the electromagnetic spectra is categorized into different region based upon the energy which radiated. So now we are going to see the one of the very important region in that electromagnetic spectra is the UV visible region. So in this particular session we are going to see the introduction regarding the ultraviolet and visible spectroscopy. As we know that the spectroscopy is nothing but the structural analysis. In the spectroscopy we get the idea about the structure of the compound, and as we know that it is the response given by the molecule when it is exposed to the electromagnetic radiation. So basically it is the measurement and interpretation of electromagnetic radiation which may be either absorbed or emitted when the molecules or atoms they move from one energy state into another energy state. So as a result of that, whenever any electromagnetic radiation they are irradiated on the compound, there occurs the change in the energy content, and as a result of that the electron from one energy level get converted into higher energy level. So in UV spectroscopy, if you see the range of absorption of radiation, it is in the wavelength of approximately 200 to 400 nanometer. So it may be in between the 190 nanometer to 400 nanometer also. So remember, the UV, that is ultraviolet wavelength, will be in between the 200 to 400 nanometer, and visible region which covers from 400 to 800 nanometer. So this particular range we need to remember in order to study the UV visible spectroscopy. So remember this particular range of ultraviolet and visible wavelength. Then in UV spectroscopy, whatever the ultraviolet radiations are absorbed, they results into the excitation of electron from ground state toward higher energy state. So whenever any UV radiations are absorbed, there occurs excitation of electrons from ground state towards higher energy state. So whatever the electrons which are present in the lower energy level, they are excited to higher energy state. So there occurs electronic excitation. So remember, in case of the UV spectroscopy, it is directly resulted with the electronic excitation of electrons. Then molecule containing pi electrons or non-bonding electrons, that is n electrons, can be absorbed energy in the form of UV and excited these electrons to higher energy molecular orbitals. So whatever the electrons present may be either sigma electrons, pi electrons, or lone pair of electrons, that is n electrons, which are present in the lower energy level, they are excited to higher energy level, that is higher antibonding molecular orbitals. So if you see, there are four possible types of transitions which you will observe in case of the UV spectroscopy. What are these transitions? It may be either from pi to pi star, that is pi homo to pi star LUMO. LUMO means antibonding molecular orbitals. Then it may be from n to pi star, it may be from sigma to sigma star, and N2 sigma star, and they can be ordered based upon their energy content. So this is the energy sigma to sigma star, which require higher energy, then N2 sigma star, then pi to pi star, and then N2 pi star. So these are the four possible transitions you will observe in case of the UV spectroscopy. So let us see what are the different electronic transitions which are taking place in the UV spectroscopy. So what are the absorption takes place in the UV visible region that correspond to electronic excitations? In UV spectroscopy, you majorly observe the transition of electrons which are placed in outermost shells. So basically the outer electrons which are present, there occurs the transition of that particular electrons, and we know that what are the electrons present, they may be either sigma electrons, pi electrons, and n electrons. Okay, so these electrons undergo the electronic transitions. So now let us see how different types of transition you can expect. So these are the different levels of electrons. If you see, these are the sigma bonded electrons, then pi bonding, then n, that is non-bonded or lone pair of electrons. So these are the present in the HOMO, that is highest occupied molecular orbitals. So these are the bonded electrons. So these are the energy levels, and what are the electrons present when they irradiated with the UV radiations, though they occur transitions to antibonding molecular orbitals. So which are the antibonding molecular orbitals? It may be pi star or sigma stars. So these are the lower energy orbitals, and these are the higher energy orbitals, and there occurs transitions. So which are the four different transitions you can expect? The transition may be, first one will be sigma to sigma star transition. So this is a sigma to sigma star, that means sigma bonding orbital to sigma star anti-bonding orbitals. So this is a, we can say this is a highest energy transition we can expect. Then second may be n to sigma star. So where is n? N is here, n to sigma star. So n non-bonded to anti-bonding. So this is a second type of transition you can expect. Then third one will be pi to pi star, pi bonded to pi star anti-bonding molecular orbital. And last one will be n to pi star. So n to pi star, it is, you can see the energy difference is quite less in case of the n to pi star transition. So remember, so these are the four transitions you will observe in case of the UV spectroscopy, depending upon the types of the electron present in that particular molecule. If we see the energy content, so which particular transition requires higher energy? So sigma to sigma star, it requires higher energy. So sigma to sigma star, you can see the distance, so it requires higher energy. Then second one is n to sigma star. Where is n? N to sigma star. So non-bonded electron which are present in the form of lone pair in the heteroatoms, n to sigma star. Then pi to pi star. Where is pi? Pi to pi star. And lower energy required in case of the n to pi star. So as there is a very less difference in the energies of these two levels, so n to pi star requires a lower energy. So remember, these are the electronic transitions that you may expect in the UV spectroscopy. So as I told you, we will see which kind of the transitions you will expect in which particular molecules. So first, sigma to sigma star transitions. So these transitions in which the sigma bonded electrons is excited to an antibonding sigma star orbitals. So what are the bonded electrons which are present in the sigma bonded electrons? They are excited to sigma star orbitals. So this particular transitions you will majorly expect in case of the saturated hydrocarbons. In case of the alkanes, basically you will observe where there is only single bonded compounds are there. The bond may be either carbon-carbon or carbon-hydrogens. So in case of the hydrocarbons or basically saturated hydrocarbons, you will expect this type of transition, sigma to sigma star transitions, where only sigma electrons are only involved in the bonding process. Then the second transition, N to sigma star. So N electrons which are non-bonded electrons or lone pair of electrons. So the saturated compound containing atoms with lone pairs, that is non-bonded electrons, are capable of N to sigma star transitions. So example may be alkyl halides. In halides also there are three lone pairs of present, or in case of the some heteroatoms such as oxygen, nitrogen, you can expect this kind of transition N to sigma star, where there is a non-bonding electrons are present, that is lone pairs are present on the heteroatom. So this kind of transition you will expect in the N to sigma star. Then next one, N to pi star transition. So these are the transition in which electron in a non-bonding atomic orbital is promoted to anti-bonding pi star orbital. So you will observe this type of transition majorly in a carbonyl group compound, that may be aldehyde, ketone, ester, etc. Or you may expect in a compound where there is a C double bond in functionality, or it may be in the C double bond S, or it may be in the nitro, etc. So these are the transitions you will expect in case of the N to pi star in such compounds, where there is a pi bonded electrons is also present and heteroatom is also present, which is containing lone pair of electrons. Then last one is pi to pi star transition. So these are the transition in which an electron in a pi electron is promoted to anti-bonding pi star orbitals. Again, in the carbonyl group also you can expand pi to pi star transition, because in the carbonyl group there is a presence of pi electrons. So in a double bonded compound you can expect pi to pi star transition. So these are the different transitions and examples of the different functionality which may results into this kind of transitions. Then we will see some of the examples. Let us see the class. In alcohols, which are the different kinds of electrons are present? Sigma, pi electron is present? No, there is occurs only sigma and n star. Sigma and n electrons. So you can expect major transition, that is N to sigma star, and due to this particular transition you will observe the lambda max or wavelength of absorption up to 180 nanometer. So you can expect. Then if you see the ethers, in ether again which kind of electrons is present? Single bonded compounds. So sigma and n. Again you can expect the major transition N to sigma star up to 180 nanometer. Then in case of the amines, again heteroatom, sigma and n electrons, again N to sigma star around 210 nanometer. Then this is an example of alkenes, where you can expect pi to pi star transition. That particular wavelength will be around 175 nanometer. In case of the alkyne, again the double bond, which kind of electrons will be present? Sigma and pi. There will not, in these two cases there will not be any n electron is present. So again pi to pi star will be the major transition. It will be in the range of 170. So the absorption increases in case of the N to sigma star, and in case of the pi to pi star you will observe the transition quite lower. So now let us say the class, that is aldehyde. In aldehyde there are different electrons. Which are the electrons present? Sigma is also there, pi is also there, and n is also there. So what kind of major transition we will observe? Pi to pi star and n to pi star. So these are the two transitions. If you see, n to pi star transitions are absorbed at higher wavelength. So you will get two peaks like this. So 190 and 290. Again, in case of the ketone, the same kind of transition you will expect. But in case of the N to pi star, let us see the wavelength of absorption, higher one. In case of acid also, there are all the types of electron space, sigma, pi and n. So this one is the prominent one. In case of the ester also, so these are the different absorption maxima you will observe in the different classes of the organic compounds. So remember which transitions are taking place based upon the which kind of electrons which are present in that particular molecule. So there are some examples such as diene system. So in case of the diene, this is a conjugated system, as there are no non-bonding electrons. As we have seen, if your compound is having no non-bonding electron, they are absorbed in between the 170 to around, let us say, 190 nanometer. But if you observe in case of the 1,3-butadiene, it is absorbed up to the 217 nanometer. What is the reason? Because you will observe the conjugation, what are the pi electrons which are present, as they are loosely bound, so there you may expect there occurs a conjugation, so that absorption maxima may shift to higher wavelength or longer wavelength due to the pi bonding excitation from pi to pi star. So this is the reason. Then we are going to see the very important terms which have very good impact on the absorption of that particular compound. So first term is the chromophore. So chromophore, chroma means color. So why some organic compounds are having color, we can easily predict based upon the type of functional group which is present in that particular compound. So what is chromophore? Basically, remember, chromophore is the entity or functionality which is responsible for the color of that particular compound. So chromophore is a part of molecule which is responsible for its color, or it is a functional group which exhibit absorption of electromagnetic radiation in the visible or UV region is called as a chromophore. So basically we can say chromophore is a functionality which is responsible for color of that kind of compound. So basically it is a functional group which is giving color to that particular compound. So that may be either carbon-carbon double bond or carbonyl group, maybe it may be nitro, or it may be N double bond. In some compounds, for example, in case of the nitrobenzene, you can see that particular compound is having very yellow color. If you take the example of nitrophenols, these are yellow colored compound. So we can easily identify that color is due to the chromophoric functionality such as NO2. Or in case of the dyes, azo-dyes are having colored. What is the reason? Because of the presence of chromophoric functionality which are present in that particular compound. Now let us understand the second term, auxochrome. So auxochrome is a group which itself does not act as a chromophore, but when it is attached to chromophore, it shifts absorption maxima towards longer or higher wavelength, along with the increase in the intensity of absorption. So auxochrome is not a chromophore basically, but when it is attached to the chromophoric functionality, it increases the absorption to longer wavelength or higher wavelength. So which it also increases the intensity in case of the height. So what are the different functionality? OCH3, for example, in case of the anisole, NH2, heterocompounds, aniline, and OH, phenols, then ethers, or NHR, amides, thiols, etc. So these are the auxochromic functionality. When they are attached to chromophoric groups, they increase the absorption to higher wavelength. So if we see the examples of or impact of auxochromic functionality which is present in some compound. For example, if we take the example of benzene, as we know that the benzene is the compound which contain only sigma and pi electrons. So it is basically a colorless compound, and based upon the pi to pi star excitation, you will observe that the absorption is in between the 254 nanometer. So if we add the NH2 group to this particular benzene, so what will happen, this particular group now will act as like a auxochrome. So it is when attached to this chromophoric functionality like benzene, it increase the absorption from 254 nanometer to 280 nanometer. You can see there is a rise in the wavelength up to 30 nanometers. So this is the impact of auxochromic functionality when it is attached to some chromophoric group. So this is very important. Then we are going to see the some shifts in the position of absorption. So first shift is called as a bathochromic shift, that is also called as a red shift. So what is a bathochromic shift or red shift? It is basically involved shift or transfer of absorption maxima towards longer wavelength. When there is a increase in the wavelength, or when you expect the peak up in the higher absorption level, so that particular phenomenon is called as a bathochromic shift. So why there is this particular phenomenon is observed? Because of the attachment of auxochrome. Just like in the last case you have seen, the this particular results in the shift to higher wavelength. So this is a basically because of the interaction between chromophore and chromophore auxochrome interaction. So because of these two interactions, you can expect there is a increase in the shift, that is also called as a red shift. So there may be the conjugation is present. So in case of the 1,3-butadiene, because of the conjugation, so two or more chromophoric, so this particular phenomena you will see. Then next one is hypsochromic shift, that is also called as a blue shift. So it is a reverse of that bathochromic shift. It involves shift of absorption maxima towards shorter wavelength. So you will get the absorption towards lower wavelength because of presence of some groups. So why this particular phenomena or blue shift? Blue shift is nothing but what? Shift towards lower wavelength. Okay. So if you remove any conjugation in the system, you can expect the blue shift, or there may be a solvents polarity which also have a very good impact on the blue shift. So in UV visible region also solvents are playing very important. So remember what is blue shift. It is a shifting of absorption of maxima towards lower wavelength. So what are the two terms, bathochromic shift and hypsochromic shift? We are talking, that is with respect to the wavelength. Now we are going to see the two phenomena, that is first one is hyperchromic shift, that is related with the intensity of absorption. Intensity means height of the peak. So this is the intensity, and this is the wavelength you can see from left to right. So hyperchromic effect is nothing but increase in intensity of absorption, that is peak height. Suppose if peak height is getting increased, so that particular phenomena is called as a hyperchromic effect. And next one is hypochromic effect. Hypo means decrease in the intensity of absorption, that is peak height suppose it this much, and if it get reduced to this much, so that particular phenomena is called as a hypochromic effect, that is intensity of absorption decreases. Let us see this particular diagram. It will help you to understand the four different phenomena are already we have studied. First one we have seen is the red shift, that is bathochromic shift. So in case of the bathochromic shift, you will observe the absorption maxima shifts toward longer wavelength. So from here to here, so this is a wavelength on this particular axis, and this is a absorption. Okay, so wavelength will increase. So this is a bathochromic shift. If it get decreased, then there is a hypsochromic shift. Okay, so these two terms, that is bathochromic shift and hypsochromic shift, they are based upon the wavelength, longer and lower. Now we will talk about the intensity. Hyper म्हणजे maximum वाढणे. So hyper is nothing but the intensity. So intensity, if it get increases, then we can say this is a hypochromic shift. Hypo, then you will expect there is a decrease in the intensity of absorption. So this particular diagram is very important. If possible, you remember it. It will help you to understand these four different effects which are present in the molecule. Now we are going to see one particular term, example of bathochromic shift. Suppose if we see the benzene, it is a colorless compound. So what happens if you add the OH group? What will happen? This particular absorption will increase. And again, if you add the nitro groups in case of the para-nitrophenol, so what effect you will expect? What is the bathochromic shift, or in terms of wavelength? Benzene, it is absorbed at 254 nanometer, phenol 270 nanometer. If you see, both these compounds are colorless one, but the moment you introduce the nitro group, what will happen? It is a group which had very good impact on the absorption. So what will happen? The lambda max or absorption maxima shifts to 318 nanometer, and this particular compound is colored. If you see, both these compounds are colorless. So this is a impact of the bathochromic or red shift. So you have to remember, in case of the bathochromic shift, the example is this one. Then hypsochromic shift. Hypsochromic shift is lowering of the wavelength. Nitrobenzene, pale yellow colored. So if you see, if you introduce again one more nitro group at 4 positions, so para-dinitrobenzene, yellow color. This one is pale yellow, this one is yellow. So you can see the color change. But if you see the wavelength, 270 nanometer, 261 nanometer. So this is the difference. So there is a lowering in the wavelength that is observed. So what is the phenomena? Hypsochromic effect shift. Now we are going to see the next term, that is chromophore interaction. So as these terms are very important in terms of the bathochromic shift. So what is a chromophore interaction? When two or more chromophores are attached together, such as in the conjugated system. So due to the greater delocalization of pi electrons, the energy required for pi to pi star transition will be reduced, and hence wavelength of absorption increase. So basically, if you remember, when there is a conjugated systems are there, for example, carbon-carbon double bond, they are separated by means of a single bond. So there occurs the extended delocalization of pi electrons, and due to this, the absorption maxima increases to higher wavelength. Suppose, for example, when there is a no non-conjugated system, the electrons are transferred from pi to pi star. But in case of the conjugated system, you can see the difference, energy difference between these two orbitals is quite less as compared to this one. So in case of the conjugated system, this particular transitions will help, and the energy required will be less. So the absorption maxima will shift. That particular phenomena results into the bathochromic shift, that is to higher wavelength. Ethene, 170 nanometer, 1,3-butadiene, 217 nanometer. Why there is increase in the shift? Because of the increase in the chromophoric groups, and these chromophoric groups are in the delocalization. You can observe this particular transitions. So due to this, you will observe this particular. So if you see, add one more carbon-carbon double bond, what will happen? See the difference, 256 nanometer. So this particular phenomena is called as a chromophore interaction, because of the greater delocalization of pi electrons. So there occurs greater delocalization, so there occurs a bathochromic shift. Then next one is chromophore auxochrome interaction. Now how the chromophoric and auxochromic interaction will take place, and that results into the wavelength absorption. So what will happen? The absorption wavelength shifts to longer wavelength. So again the bathochromic shift will you will expect when lone pair of electrons on the auxochrome get involved in the resonance with the chromophore. Let us see the example. Nitrobenzene having absorbed at in the region of 270 nanometer. Suppose if you introduce the amino group at para position. As we know that nitrogen is having lone pair. So what will happen, lone pair of electrons in this particular auxochromic group will involved in the resonance. So what will happen, you will observe the delocalization of electrons, and as a result of that you will observe the wavelength of absorption is increased from 270 to 381 nanometer. So this is due to the involvement of lone pair of electrons in the resonance process. So what happens, you can see this is a auxochrome and this is a chromophoric interaction. So due to this auxochromic and chromophore interaction, the wavelength of absorption shifts to longer wavelength. So hope so you have understood this particular concepts related to the UV spectroscopy. This is a quite longer video, but these terms are interconnected to one another. So they have I have tried to explain with the help of some examples. Go through this particular session. Definitely this particular terms will be important in order to understand the UV visible spectroscopy. Thank you very much. See you in the next session.